Okay, so let's start. Last time I told the following thing, that there are such fields e to square root of 2 b phi and e to the square root of b e inverse phi. So their dimensions are 1, and they are called screenings. And if you want, if you, for example, want to compute conformal block, if you want to, if you don't have this screenings, then we can compute only conformal block with some alpha 0, alpha 1, alpha 0 plus alpha 1, alpha t alpha 1, and here something like, well, it depends on which charge we write, and the charge for dual vector, or but let us write that if don't dualize anything, then it will be alpha 0 plus alpha t plus alpha 1. So we can also insert only one screen, and in this case we can compute a conformal block where here it is alpha t, alpha 0, and we can draw some picture. So there are points 0 and t. So we want to say that this charge is alpha 0 plus alpha t plus b. Here we have alpha 1, and here we have alpha 0 plus alpha t plus alpha 1 plus b. So if you want to compute a conformal block like this, then we need to so we need to draw some picture to understand where to put this screening. So we have points 0, t, 1, and infinity. And if you want a charge of this to be alpha 0 plus alpha t plus b, then of course we need to say that the screening is integrated between these 2 points. So if if we are afraid that this integral will be divergent, we should integrate it over some programmer contour. So is it that one? No, maybe it should be more complicated. So one contour is just from 0 to t, but if we are afraid that this integral is divergent, we can take something like AB, A inverse, we can take this contour, and then it will definitely be convergent, I think. So this is called contour because it goes around 0 and t in two opposite directions. So a monodromy of a function is trivial. So the integrand here is on this integral over some contour, like 0t of what of t to minus 2 alpha 0 alpha t 1 minus t to minus 2 alpha 0 no 0 alpha t so it is just some trivial prefactor is independent times z to minus 2b alpha 0 yeah 1 minus z 1 minus z to minus 2b alpha 1 times z minus t to minus 2b alpha t dz. In this case, it equals to hypergeometric function. So it can be computed somehow. So as I told you, it is somehow related to that other hypergeometric function, which is obtained when one of these fields is degenerate and other fields are arbitrary. But this also happens if we ask this conservation, if we want to violate this conservation condition in this point by 1. But now, so in principle, these integrals can be used to obtain some more or less explicit expressions for this conformal blocks. And let me show one of the examples of such expressions. So C equals 1 example. No, maybe first let us talk about the choice of contours. So we see that if you want to evaluate this conservation law around points 0 and t, we should integrate around integrate the scans here. But at the same time, we can try to do this around, for example, 1 and infinity. So we can let me think. Mm. So here we see that this field at infinity was also shifted by something, and in principle we can do like this. We can place n1 contours around 0 and t. So and another so it's from 0 t, and another and two contours around around 1 and infinity. So then corresponding charges will be the following. So here it is alpha 0, alpha t, alpha 0 plus alpha t plus n1 b. Here it is alpha 1. Here I don't like this dual picture. So also we should write something of this kind. Here it's alpha 0, alpha t, and so this intermediate dimension is alpha 0 plus alpha t plus nb plus n1b. and here we should say that this one is alpha 1, and we should preserve the overall conservation. So this charge should be so alpha infinity should be there should be in this condition that alpha infinity plus alpha 0 plus alpha 1 plus alpha t plus n1 plus n2 b equals to so this should equal to q, and so it will find this alpha infinity in terms of everything else. So why I'm writing this formula is to say that originally we had two conservation laws at this point. When we had scannings around 0 and t, we can break one of these conservation laws. And add one discrete parameter n1. And if we insert these integrals around both cuts from 0 to t and from 1 to infinity, we now have three continuous parameters and two discrete parameters n1 and n2. But the overall count is 5, as in principle we would like to have for a generic conformal block. And why is it interesting? Because we can try to consider the limit when dimensions in this conformal block go to infinity. So it is so-called Seiberg-Witten limit. So central charge in this case can be fixed. And deltas go to infinity, which means that alphas go to infinity, and b is fixed. And why is it interesting? Because in this case we can say that alphas are much much larger than b, and then this discrete freedom becomes more or less continuous. So if you now have this integral with scannings from between 0 and t and 1 and infinity, so so this conformal block can be written as so conformal block can be written as the integral so from so some integrals from 0 to t and 1 integrals. Then n2 integrals from 1 to infinity. and 2. And there is an expression like product of disease t2 minus 2 alpha 0 alpha t 1 minus t. Like, well, I don't want to write this t-dependent, t-only dependent part, so let us write the essential part. So it is a product of z2 minus 2b alpha 0 zi 1 minus z2 minus 2b alpha alpha 1 z minus t 2 minus 2b alpha t, and a product over I less than j zi minus zj 2 minus 2b squared. Like this. And as I told, we want now to send alphas to infinity. So let us say that alphas will be proportional to some so alpha i's are some large n times alpha I tilde, and this two n's n i's will equal to n times some xi. Probably it is safe to use this notation. So they also go to infinity in the same way. So and this xi's are fixed. As n goes to infinity. So this conformal block equals to the integral in dzi's and now we can rewrite this as e to sum over I minus bn log of zi alpha 0 log of zi plus alpha t log ci minus t plus alpha 1 log of zi minus 1 like this minus 2b squared sum over ij log of zi minus zj from for I different from j. So and now if you introduce the density of this eigenvalues, we can write that it is integral like dzi. So if we now say that density of the eigenvalues is equal to 1 over n, so by definition, sum of and delta z minus zi. So then this integral equals to e to those define potential. V is let us define it as 1 over b. V of c 1 over b. This one alpha 0 log of z plus alpha t log of z minus t plus alpha 1 log of z minus 1. So this integral now is rewritten as minus b squared and squared integral of v of z rho of z dz minus b squared and squared integral dz w rho of z rho of w logarithm of z minus w, right? And if now try to so it is a kind of matrix model. So, but so. And this can be solved as we solve the matrix model. So this density should be locally preserved in a sense that we should keep the integral of it over the first interval from 0 to t and over the second integral from 1 to infinity. So possible variations, if you want to compute something using saddle point, possible variation is by derivative of some function in z. So let us say that rho is modified by rho plus some dz of some function delta, well, epsilon dz of phi, some function phi. And so if you perform, if you perform this variation, then what happens? So let us call this this expression minus b squared and squared S of rho. So S of rho plus epsilon dz of rho, or dz of phi, equals to S of rho minus integral from oh, so here it should be absolute value probably, minus integral v prime of z phi dz here minus 2 integral of phi of z rho of w over z minus w dw. Right? So and this should vanish for all phi's. So delta s equals to 0 is equivalent to v prime equals to minus 2 v prime of z equals to minus 2 integral of rho of w over well, let us change here the sign. Oh, maybe it's fine. Minus 2 rho of w over z minus w dw. And so we have such an equation. And this equation is satisfied for z inside the oh, so let me think. Principal value integral, and this is satisfied for z among the eigenvalues 0 to t, known as 1 infinity, because all the eigenvalues in our integrals are placed in these domains from 0 to t and from 1 to infinity. So we perform some local perturbation of the density of these eigenvalues, and so this perturbation of the density has support from 0 to t and from 1 to infinity. So we have. Because we have chosen these integrals in such a way. It is so in principle they are integrals in the complex plane. So we can so if the values of alphas are very inconvenient, we can in principle imagine that there are some programmer contours around these points 0t and 1 and infinity. But if we are in such a domain that these integrals are convergent at the boundaries, we can just exclude these programmer contours and reduce them to integrals over these intervals from 0 to t, from 1 to infinity. It's only a question about convergence. So is it fine? Mm. But even if we integrate over the grammar contour, then we want to find this saddle point condition, and I think if we ask these alphas to be real, then the saddle point condition should also be on the real line. Okay, so sorry, it is a principal value integral, which is important. Like it was here, because it comes from sum over I different from j, and it is still here. So we have this condition, and now let us think about solution to this condition. So, who is this expression? It is so. Let us introduce so-called resolvent. R of z is equal to the integral we can write either from 0 to infinity, or write explicitly that it is over the support from 0 to t, 1 and infinity. Rho of w dw over z minus w. And so it is some function with which is homomorphic everywhere except this union of branch cuts. We also know that R of z, when z goes to infinity, behaves like n1 plus n2 over n over z. So we know this. So what is the meaning of this saddle point condition? So this principal value integral is actually a sum of resolvent a little bit above the real line, a little bit below it. So we can write that v prime of z equals to minus r of z plus I epsilon minus r of z minus I epsilon for z on this union of branch cuts from 0 to t, union 1 infinity. So if you now consider and this v prime of z is single valued. So let us now consider the function r tilde of of z is v is 1/2 of v prime of z plus r of z, yeah, plus r of z, and uh, consider r tilde of z squared. So is it clear why it is true? Because we have first condition that we have the first condition on this one, which actually describes the jump of resolvent when we go through this curve from 0 to t and 1 to infinity. But if we try to cross the real line somewhere away from the start, then we will have, so it just continues there. R of z plus I epsilon equals to R of z plus I minus I epsilon when z is not in this union of intervals. So if we combine this together, then we see that first condition tells us that R tilde of z plus I epsilon equals to minus R tilde of z minus I epsilon when z is in this interval. And right, so and conclusion of this is that R tilde of z squared is a single values. So is it fine?
Why the set, first of all, like the fact that we split the derivative of the potential in that way is just a choice that we make.
No, but
First, that we have.
no. What do you mean? we don't have any choice here. We just wrote that principal value of this integral. So this is this statement that principal value integral of 2 times principal value integral rho of w over z minus w equals to integral rho of w over z plus I epsilon minus w dw plus integral of rho of w dw z minus I epsilon minus w. So is it fine? Right? So, are there any questions? No? Problem? Maybe it's possible to turn on that light. Oh, sorry. Since we have this statement that it is single valued, now we can ask about its asymptotics. Also taking into account this notation, we can write that this one equals to x1 plus x2 over z. So let me think. Oh, here I was actually no, let me think. Probably here I was actually a line because it can turn out that saddle point, and it will turn out that saddle point for this integral will be placed on some deformed interval. So. Yeah, I just thought about the answer. Let me write that it is integral over some contour which contains these eigenvalues. So I will not specify it now. It will be some deformation of this intervals from 0 to t and from 1 to infinity. So it is actually more complicated, especially in the complex situation. So let me write. So it is. So it does not matter for all these computations, but we should write some abstract interval here. Mhm. Uh, so and so we know that now it is a single valued function, and we want to find its asymptotics. So so we can write that so this r tilde squared of z should uh, I don't know, maybe it was better to write uh, mm, so this is written here. Maybe it is better to introduce this function with a factor of 2. So let me write that it is 1/2 times r tilde equals to this. Mm, so we know from this definition, since we are adding to it, so since it is r plus v prime, we know that r tilde of z is oh, actually I also missed a factor of 2 everywhere, but it is not important probably, or it is. Mm. Oh, it is important. There should be no this factor of 1/2 here. Mm. So if I start with a correct factor of 2, then we see that this r of z squared around 0 should behave like alpha 0 over b squared over z squared. Uh, it should behave like alpha t over b squared over z minus t squared. Like alpha 1 over b squared over z minus 1 squared, right? And like so if you think about infinity, we should be more careful, because now there are all these alphas which come from the potential, and there are also x1 uh, x2 from this asymptotics. So here it behaves like and there is one half from the potential, and so it is alpha 0 plus alpha 1 plus alpha t plus alpha 1 divided by b, all of them, plus well, maybe I should have included this b in the definition of something, maybe in the definition of rho, because I don't like that it appears everywhere. So maybe let us maybe include it here, because I don't like this alphas divided by b and so on. So if we do this, then we don't need to write this b here, and it disappears also here. Now it's much better. Well, this is just alpha 0 of alpha t, but it will reappear here as expected. So alpha 0 squared, alpha t squared, 0 plus 1 squared, plus b x1 plus x2 squared over z squared. This is when z goes to infinity. And now the question. Uh, how many such functions can we write such that these functions have such an asymptotic behavior? So this is some function. This r tilde of z squared can be written as what? As some combination of first order poles. Sum of alpha I squared plus ci over alpha I squared over z minus zi squared plus ci over z minus zi. I equals 0, t 1. So there is some again some general answer. So for a function which has poles at 3 points 0, t, and 1. But we have this extra condition about behavior at a infinity. So we should write what's going on there. So so this R of Z is sum of alpha I 1 over Z squared plus 2Zi over Z cubed, which is not important already, plus Ci 1 over Z plus Zi over Z squared, and yeah, that's all. So there are the following conditions following from here, that sum of Ci is equal to 0. Sum of Ci times Zi equals to what? It is coefficient in front of one of Z squared. So it should equal to delta to this. Let us call this alpha infinity. Should equal to alpha infinity squared minus alpha 0 squared minus alpha t squared minus alpha 1 squared. So it means that there are three parameters restricted by two conditions. And so the general formula for this R of Z can be written like this. So it should contain one free parameter, and it looks like alpha 0 squared over Z squared plus alpha t squared over Z minus t squared plus alpha 1 squared over Z minus 1 squared and on this contribution, so then this term which will take care about asymptotics at infinity, it is z minus 1 times alpha infinity squared minus alpha 0 squared minus alpha t squared minus alpha 1 minus alpha t squared. So we can check that it has only first order poles that and 0 and 1, and it cancels this, so it makes a cubic term at infinity correct. And now the last term, which is responsible for parameterization of this first order residues, and it looks like some number u over z minus t z minus 1. So this is r tilde of z squared. So there is and this is called a Seiberg-Witten curve. And and also this expression should also remind something else. Namely, it looks like expectation value of the energy momentum tensor in presence of four primary fields. Actually, since we have here alpha squared and dimensions are with opposite signs, so it is kind of minus expectation value of this energy momentum tensor alpha t of t, alpha 1 of 1, or alpha infinity of a infinity, divided by the square later.
We see that like this is like an elliptic curve. One should take the inverse of 1 plus square.
Why inverse?
When one writes like elliptic curve, the equation is something like w squared equals to some cubic polynomial in z.
Yes, but in this case, it is a different parameterization. So, namely, let us look at the case when all this alpha is equal to 0. It means that we consider a conformal block with fields of with this external fields of finite dimension, but dimension of the intermediate field goes to infinity. So in this case, it is it is r of z equals 1 over square root of this thing. Right? So it is a traditional elliptic curve. But if we now turn on this alphas, then these points which were before branch points are just some arbitrary points which are singularities of R. And branch points will be zeros of the numerator. And the numerator is some quartic polynomial because say when we try to bring put this into a common denominator, each of these terms will produce some quadratic polynomial, right? And also actually also this will also produce some quadratic polynomial. So a position of its zeros, it's something more or less unpredictable. Like, of course, we can solve a quartic equation, but it is not something nice. And in the limit, they go to points 0, t, and 1. So it is some picture of this kind. And of course, we can bring it to a canonical form. We should just perform a fractional linear transformation which maps zeros of this polynomial to 0, q, 1, and infinity. But it is it will be something that contains fourth roots of maybe third roots, like its expression which involves roots of of some generic quartic equation. So it's not nice. Oh, so so what can we say? So can we say? There are also there are these cards. So one card, so there is 0t, 0t, and 1 in infinity. And there are those branch cards which are in generic situation somewhere near these points. So we remember that that intermediate dimension in the conformal block is equal to alpha 0 plus alpha 1 plus alpha t plus n 1. So if we now want to find who is u, if we want to relate it to this intermediate dimension, we should remember about that condition, namely, so let me think. So all the eigenvalues are in this contour, and so let's call this contour some kind of call this a cycle. So it is kind of Seiberg-Witten equation. That x1 bx1 should equal to the integral around this a cycle of our tilde of z dz. To be precise, divided by dz over 2 pi I. Is it clear why it is? So, is it? So this is because if you take the definition of this resolvent and integrate it around the branch cut, it will give uh, so if you say that it is a sum of 1 over z minus zi, such contraintegral around the position of zeros in this branch cut will give the number of them times 2 pi I. So if you divide by 2 pi I, it will just give the number of numbers also multiplied by b because of the definition, right? Mm. So and but uh, and if you write this equation, then it allows us to relate u and x1. So u was some unknown number, and x1 was the parameter of conformal block. So it allows us to express x1 in terms of u. So 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 solving this equation, we can say that u is u of x1. Right? And and I actually want to do another thing. So at this moment, we computed the variation of this this functional only under small changes of the eigenvalues. But it is also interesting to compute to compute the dependence of this functional of rho when we change axis, when we move one eigenvalue from one cut to another one. And so and in this way, we will get another equation which will express derivative of this functional in terms of some other integral. So let us do this. So it's like an multi-cut matrix models. Mm. So, so basically, I want to do the following. So take one eigenvalue from this cut, from 0 to t, and move it here. So let us return to original. No, I'm trying to think if we need to study individual eigenvalues, or we can do it. We can do it simpler. Uh, so. Mm, Well, we can do it simpler. We can say that our phi, which we use to compute this expression, we want to move this eigenvalue uh, somewhere here. To do this, we should say that rho transforms to rho times epsilon, and let us say that this is some number b, some position a, and this is some position b, and we add to this rho a indicator function of so derivative of the indicator function so it will so here we have x1 times n eigenvalues, here we have x2 times n eigenvalues, and if we do this, it will change x1 by epsilon. So it corresponds to x1 to x1 plus epsilon, x2 to x2 minus epsilon, right? So if you perform such a transformation, then let us say use this formula. Uh, so uh, 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 S transforms to S plus epsilon Oh, actually, I forgot epsilon here. Plus epsilon minus epsilon integral for v prime of z chi v prime of z dz v prime of z plus 2 integral rho of w over z minus w dw phi of z dz chi of ab. So now this is essentially integral from a to b. But since we know that this expression vanishes on the branch cuts because it already solved that equations, then only the only remaining part of this integral, so it is s minus epsilon integral from branch cut from the first branch cut to the second one. Let us introduce some notations. Maybe let us call this E2 or no, what's the notation? Let us call it ET and EE1. So integral from ET to E1 of and now let us look at this expression. It is essentially 2 times our resolvent, 2 times our tilde dz. So it gives us the second Seiberg-Witten equation, which tells well up to some sign maybe, or maybe the sign is correct. I don't know. So the second so so it tells us that d over d d bx1 probably, yes, bx1 equals to df over dbx1, or actually log f. Let us write that it is ds over dbx1. It equals to the integral over b cycle of this r tilde of z dz. So b cycle is here. So so it goes from this point to this one, and then goes to another sheet of this curve. And maybe with a minus sign, let us write it and then check if it is correct or not. And also, so we have this formula for S, but a conformal block itself equals to some prefactor which depends on t, but it equals to t times to some power 1 minus t to some power times e to minus n squared s. So if we want to compute this limit of conformal block, what we need to do? We need first to write this Seiberg-Witten equation and express this parameter of spectral curve or Seiberg-Witten curve in terms of this period. So we express intermediate when express this parameter in terms of the intermediate dimension. Then, when we have this dependence, we solve second Seiberg-Witten equation to compute the value of S, and we see this symptotic behavior of conformal block. And also, what can I say? We can also prove it is not so obvious, but it is true, and it also follows from this intuition that it is expectation value of the energy momentum tensor. So this intuition tells us that this equals to t1 minus t ds over dt. So we can check, we can prove this independently, but it tells us what, that if we try to shift t in this formula, then how to say it? We know that if we consider this conformal, if we consider this conformal block as a function of t, then coefficient at 1 over z minus t is proportional to derivative of the logarithm of this conformal block, because we divided by conformal block. And if you now check the residue at z equals t of this expression, it gives precisely that one. Oh, actually, maybe. No, this one has 0 residue, so so the only residue at z equals to t comes from here, and it is actually, and it should be ds over dt. Maybe plus or minus. Maybe with minus sign, because no, oh, I want to write it to t minus 1, but I'm a bit lost in the signs, because here we have, so I don't know if it is, so as it is written now, it's a station value of energy momentum tensor, and it's also, it is also a little bit lost if this conformal block, if this has a logarithm of conformal block or minus logarithm of conformal block. So in principle, it can be plus or minus here. I cannot track the sign. and now let us consider some simple example of this phenomenon. So if mm, so if all alpha is equal to 0, then this r tilde of z equals to square root of u over z over square root of t of z t minus z minus t z minus 1. It is a holomorphic differential. So let us multiply it by dz. And so um, now I will say that its integral around the a cycle should equal to bx1. And it tells immediately that there is only one holomorphic differential on the elliptic curve. The consequence of this, immediate consequence, is that r tilde of z d z equals to bx1 times canonically normalized holomorphic differential. Bx1 times canonically normalized.
So by canonically normalized, you mean a form that has qx like qx 0 over a and instead like qx 1 over a and qx 0 over b.
No. It has a period 1 around A, and some period, like essentially the period of elliptic curve around the B cycle. Because, so maybe, yes, exactly. So bx1 times omega 1. So this one is, well, I wanted times omega, and this omega is canonically normalized. So and this uniformization, what can I erase? Probably I can erase this. So if you consider the map from some point, I don't know, for example, from 0 to z omega 1, to the uniformization map. So it maps the stores to this parallelogram. So from 0 to 1, it corresponds to a cycle, and from 0 to tau, it is a B cycle. So if we now write the second Seiberg-Witten equation, so then find that ds over oh, actually I forgot about this 2 pi i's. Probably so in this parameterization, this integral without 2 pi I equals to 1. So so it means that we should write 2 pi I on the right hand side here. Sorry. So r tilde of z dz equals to 2 pi I b x1 times omega. And this is canonical, and this omega is canonically normalized. So integral of omega over a cycle is 1. Integral over a b cycle is tau. And so now let us write a second Seiberg-Witten equation, and it tells us that ds over dbx1 equals to 2 pi I bx1 times tau t minus t, and then so s then equals to minus pi I bx1 squared times tau. And if we now recover the formula for conformal block, so maybe yeah, it should be correct, I think. Maybe I missed some signs on this way. So let us see what we get. So then conformal block equals to e to pi I tau Actually, I don't like this sign which we obtained. And let us check if it can be missing somewhere or not. Hmm? Uh, no, no, it is fine. I'm just trying to look for possible factor of 2. So at this moment it seems that it is missing, but let us actually check. No, actually there is another problem because this one is minus dimension. Mm. Hmm. Ah. Mm. No.
Maybe as a factor 1/2 from the beginning.
I don't know. So, and there is also some minus sign, and because in our convention, uh, so in this convention, uh, ah, uh, wait. Hmm. So what we should get is this expression n(bx1 squared) is equal to minus delta, because it is alpha times q minus alpha. So namely we get here e to the minus pi I delta. pi I tau delta. And it is not what we want. It would be much better if we had e to the 2 pi I tau delta. Because so why is it so? Because let us compute the period of the differential when t goes to 0. So when t goes to 0, so a period of omega is so dz over 2 pi I square root of z minus t around the a cycle times 1 minus z. So this is of order 1 because these 2 points glue together, and it's like to compute residue of 1 over z at 1. But another integral from t to 1, so there are two singularities which pinch this other integration contour from 1 to from t to 1. So and so so we need to compute the integral dz over 2 pi I square root of z minus t from t to some point of order more or less 1. Oh, no, from t to epsilon. So we integral over b cycle of this of this differential in the limit t goes to 0 should be split into a singular part and something regular. And So the change of variables should be something like z equals to a t hyperbolic cosine of x of psi. And so in this integral, and in this integral, this should be hyperbolic cosine squared. Just the hyperbolic tangent of some eta. Oops. So sorry, it takes too long. So, this one is so if you compute this integral, we should integrate twice. So this Yeah, so I want to say that. So what I'm doing now is I'm trying to compute the asymptotics of this tau when t goes to zero to see that it is so that we cover correct behavior of conformal block. And to do this, I separate this integral around near the on this cut which shrinks. This is this first integral, and the second integral from some more distant point, when we can say that z and z minus t is the same. So, and now there was only a question how to compute these integrals. So after such changes of variables, these two integrals turn into like 4 over 2 pi I, and here we only need and also there should be some factor of I, and because one of these terms becomes negative, namely z minus t becomes negative, so there should be something that cancels this I everywhere. So we have 2 over pi, and now these integrals are so this first integral equals to psi from like in the variable z, in the variable z it should be from t to epsilon, and this eta, which goes also from so it goes from epsilon to 1. And now let us compute the values of psi. So when t when z equals to t, this psi equals to 0. When z equals to epsilon, and if this epsilon is big enough, then so this equals like 2 over pi. On the upper interval, we can say that this hyperbolic cosine can be replaced by just one exponential. So if epsilon is much bigger than t, then this can be written as uh, a log of this epsilon over t, 2 square root of epsilon over t. So this is asymptotics. And let us compute this second part. So here on the upper limit we have eta equals to 0, and on the lower limit we have eta equals again to so actually we should have changed sign here probably. So we will get a logarithm of 2, 1 of square root of epsilon. So the result of this is that this bicycle integral, so maybe I will use this blackboard. So this bicycle integral. So it should be proportional 1 over pi log of of 16 over t. No, well, there is still a question about the factor of phi, if it is here or not. So, so it seems that I missed some factor of phi. No, I should have kept all the i's because this expression, when z is from t to 1, it is positive. If it is written like this, so yes, it is 2 over pi I here. It's everywhere. So it is 1 over pi I. Well, again, the sign, so it should be something like plus minus. Or maybe it is fine. No. And no. Again, and this problem with sign, but up to the sign, it should be equal. So this tau should behave like I over pi logarithm of 16 over t. I think, and so the moral of this, maybe well, maybe it means that this formula is so that a correct formula should be this one: e to the pi I tau delta. So again, a missing sign. So the moral of this computation is that this conformal block behaves like t to delta, as it should be. So it is it is a kind of the leading term in the conformal block, and full asymptotic expression for this conformal block is achieved by a replacement of this term by modulus of elliptic curve. Yeah. Sorry for running out of time. And actually, we will see an example where this formula in fact becomes exact, but for some specific dimensions. So the dimensions are 1 over 16, and uh, uh, the meaning of this is that if you take some explicit formula which has this form and it contains fixed dimensions, then if you sum this dimension, if you send intermediate dimension to infinity and keep external dimensions fixed, then from the Seiberg-Witten theory point of view, it corresponds to the limit alpha is equal to 0. So, let me check the recording. So are there any questions? Okay, so thanks for your attention.